Hello everyone, this is Professor Ma and this is introduction on the sections on line integrals in the work. In physics we have a concept that if we apply a force to objects in the same directions and we move the objects by a certain distance d, then multiplying the force times the distance, the displacement, I get that's the definition of total work. Okay, so uh, and notice if I want to, and this is interpreted as a dot product. That is, I have a displacement vector over here, u is 5, and then I have the force vector, which is the red one, is 10, and if I take the dot product, which is just multiplying in one dimension case, I get the 50 foot-pound. These turns out to be one very useful interpretation for a dot product because this turns out to be the case if I expand these two into two-dimensional vectors. Over here, I have a force which gives the directions, and the length of the force is the measurement of the force. And then I have the point P to Q, which is the displacement of the object by the force. Since the force and the directions of the displacements of the objects are different, so the force act upon the object directions is not the entire F. So what it is in physics, it turns out to be the projections. Okay, so we have the vertical projection, and that's the force that's applied in the same direction as PQ. Uh, Now, therefore, the amount of works done is the vectors times the length of the vectors force in that directions times the distance P to Q. The distance from P to Q over here is here. And the projection force by trigonometry is the length of F times cosine of theta. Okay, so that's the length of this component force. But this, if you recall, is also the dot product of the vectors. Now, if we interpret as a vectors, dot with a unitized vector of PQ, that is the vector PQ, I shrink it down to length one, unitize it. Okay. And this is the red part, and times then the PQ outside, the length of PQ, and this cancels out. And what I'm left with is the work that's required for the displacement of PQ uh, done by the vector capital F is the dot product. So that's one interpretations of dot products. Okay, is in of vectors is the force. One of them is a force, and the other one can be interpreted as a displacement. Then the dot product is how much work is done for the displacement of the objects. Okay. And that is very useful. And what we would like to do, okay, is now to calculate the total amount of work of objects, okay, work done on the object move in a force field, in a vector field, what we call. That is, suppose now we have, like for instance, a current, and which the current has different flow in different direction with different force, and we try to swing in the current from one point to the other, or how much work has been done. Okay, or if the current push something from one point to another point, how much work is done by the current. Well, to do that, as the current has different force at different positions, so we need a representation for force. Hence, we have this notion of vector field. What's a vector field? A vector field is well, let's start with a two-dimensional vector field. A vector field, basically, we assign each point on the plane a vector. Now, how do we assign it? What kind of formula we write? Well, we just write as some capital F at a point. This is a point x, y on the plane are associated with some function x the I components of the vector and the j component of the vectors. Okay, and for example, I can define the vector field f at a point x, y to be the vectors x, y itself. So at different location, I assign at 1, I assign to it little arrow pointing at 1, at a point 1 minus 1. So I can literally imagine at a point 1, 1, I stick a little sticker that's a vector 1, 1 at the point 1, 1. Okay, at a point, let's say 1, 3. This is the vector 1, 3. So I stick the vector 1, 3 there. 1, 5. This is the vector 1, 5. So I stick the vector 1, 5 there. So as I go out in this, you can see the vector along this point gets flatter and flatter. And so these are some of the vectors which, if you plot all of them, you will find that this is a expansion vectors like that. Okay, kind of explosive vectors like these. And here is another one, and we can plot some of them, and you can, I only plotted these as they go out. Again, they flatten. So, and then here are some nice pictures you can see if you Google vector fields. And vector fields are also the lines. If you put magnetic fields and magnets underneath the paper with then you put powders, iron powder, and then you form these lines, and those are, you can represent those as vector fields. Or in 3 dimension, you ever see like undersea world, you see those fish swirling like a cloud. Well, you can imagine each one of the fish is a real vector, and that what they form is a vector fields. As they swim around, and then their motions, and we can describe how the vector field change. So a lot of applications for movements and stuff like that. But we're going to interpret all these vectors as force. Okay, and we want to calculate objects that move from point P to Q, and all these red vectors are from some defined vector fields. Okay, there's a vector field underneath, and it moves an object from point P to point Q. We want to calculate the total amount of work in this vector field, under this vector field. Okay. So the way to do it is, so the integral will come up with to do these. Again, I'm going to add up a bunch of little pieces of works done on little pieces of movements, and the integral will come up with, we call that the line integral over this curve. Okay, and to do actual calculations, we need to bring all the algebra back to the parameterization. That is how this curve is described, and usually is described in terms of parameter t. So we start out with a curve. So that's given by xt, yt, and t goes from some place, and t goes from A to B, and in this case, and the P and Q are the endpoints of the curve. Okay. Oh, we assume everything from here, everything is differentiable, so we're not going to worry about differentiability and stuff like that. Okay. And now we have a vector field on this screen. Okay, and then these are some of the vectors situated on the points on the curve of the path. Okay. And basically, to calculate the total amount of work, we did the following things. Okay, we cut the time t from the variable t into little partitionlet, and between ti and ti plus 1, let's say the point move from the object is displaced from here to here, but we kind of pretend it's displaced in a direct line fashions, and this direct line I can kind of approximate it with a tangent line, if you like. It's a derivative. So we can use that as sort of the displacement vectors of that is how much the object is displaced. Okay, as a straight line. On the other hand, I know what the vectors forces at that point. So hence, all I have to do is dot this. This is the derivative c prime at t. Take the derivative x prime t, y prime t, and plug in the t, and you can find out what the derivative of is. And basically, all I have to do therefore is dot f. To displace, all I have to do is dot f with the displacement vector c prime of t. Okay. Now, of course, this is over a tiny amount of time, dt. Then I add them up. So these little displacements of vectors of all the works down on little straight line pieces. Each one is a dot product. So if you go through the calculations and in symbols, you end up with this conversion, basically pulling everything back into t, which is something we can integrate. Okay. We also write this as if I write c prime of t as the dc dt, then we write that dc as for simplifications. So sometimes you will see that. Okay. You will also see that. Is that without the reference all the way back to t. Okay. And this is a notation which we haven't encountered before. That is actually we draw, we put a seed on this and indicating this is a curve, and then the actual integrations we have to do is go back all the way to the formula in t to do the calculations. Okay, and here are examples how we do that. Oh, by the way, this is called the line integral of the vector field over the curve, the path, the displacement of c, okay, which is the work done. Okay. One thing we're not going to prove is that given the curve, the path, it doesn't matter how you parameterize. My size is differentiable, is nice, then you will get the same answer for the total amount of work. Okay, this is a very important result, but we're not going to prove it. And so here's the calculations. And so in the calculations is that all the information about the curves, well, a lot of time about the path and the vector field, they are given in x and y's. So in the calculation process, we have to parameterize the path. In this case, the path is a parabola given x and y coordinate. You go from the formula is this formula. It goes from this point. From this point to 1, 1. Okay. So the standard parameterization of a curve like that is you set x to be t. Okay. If the formula is the other way around, x equal to g of y, then you set y to be t. Okay. and yt. It doesn't matter which is which. It's easy if it's a function if one of the other. It's harder if it is not. Okay. To parameterize it. So in this case, it's easy. So we're just going to set, since it's a function, we're just going to set the x to be the t. Okay. And then if x is t, then where does the x comes from and where does it start from and where does it end? That's the value of the t. Okay. And then what's y? Y is the formula t squared. Is as is. So this will be the parameterization of C, the curve C of t. But the standard way to do it. Okay, once we have what the x component, y component are, now I can replace everything into t. Okay, remember what we have to calculate the integral first of all from -2 to 1. Okay, since we're going to integrate the answer, come up with the answer of total work. So it's going to be integrating t from -2 to 1. Okay, what's in the middle? The middle, remember, is f dotted with c prime of t. So both are vectors. What's f? F's right here. F is xy, x minus y. Okay. And what's C prime? C prime, everything's over. C prime is already in T, so C prime is going to be 1 to T. So I'm going to dot this, but I don't want X, Y, so I want everything back in T. It's T square, T, so T squares, everything back in T. I got this. T cubed, T minus T squared, that will be 1 into T. And that I'm integrating from -2 to 1, and that's the total weight. Okay, so this is what I meant. You need to create the parameterizations for the path and then convert the x coordinate into the parameter xt, y coordinate, yt, and everything back to t. And the theorems, if you parameterize everything backward, okay, then you will get a negative result for the. So yeah, so we have a notion of negative works and positive works. And this notation used for the curve itself has two components: the I component and j component. The vectors. The force field, which is F and G, it also have two components, okay? And the X, the I component and J components at each point, right? And so the F, the X component of the force, okay, and the displacements control the X component of the displacements, and the Y components controls the y coordinates related to y coordinates. So we come to realize two different integral, the component integral, if you like. Okay. So when we do these calculations, we can break it up into these calculations that's which we done before into two integral. Okay, that is y integral is the f integral with respect to dx is x prime t. It's everything in t with dx prime t dt times this, if you like. And the dy, if you like, this is going to be y prime of t times y prime of t dt, if you want all the way back to dt. But we write in this way, the f components, I components, line integral with respect to the x components of the parameterizations. The, oops, I should have used the blue one for the others. The x components of the vector fields, line integral over the x component of the parameterizations. Okay, as one part of the total works, and the other part is the y components take an integral with the y prime dt. Okay. So a lot of times you see this separated to these two distinct portions. So for example, problem we pose like that, and then it says, oh, it's dy, therefore it's you're going to parameterize the curve, and then you look at the y component. Okay, so here we go. And the curve can be parameterized as, again, xt, y, e to the t, because the functions. Okay, and my function h of xy is x times y, so in t is that. And then dy is y prime dt. And so you look at y, and so y prime dt is et dt. And so with this, we can put these together. Okay, and then it's either do integration by parts, and then they get the answers. Okay, and then if you got that ideas, then these are for vector fields in two-dimensional space over a path in two-dimensional space. So these are examples in 2D. And in 3D, everything exactly the same, except you have a z component. So you have a vector field f of x, y, z, f, g, h for three-dimensional vectors. And then you can do the component line integral if you like. Okay, over the curve, parameterized by three components, x, t, y, t, z, t. And everything the same. So I'll leave it to you to read that. And let me skip to an example on page 86. And a lot of time we want to compute the total works of displacement down over a closed loop, goes around, come back to itself without crossing itself. Okay, so like this triangle over here. And then the way we do that is we, of course, compute the program, or have to compute that in three separate pieces over here, as you will see. And so we did it in three separate pieces. In this, it turns out, is the topic for next sections. That is what? To integrate over a closed loop, like this triangle over here. There's a green theorems, which is next section. Oh, a lot of time can be done easily. It turns in this all this line into a double integral over the triangles itself. And so we'll talk about that next time on Green's theorems. Okay, that's it. Bye-bye. Bye.